Let's now talk about number 5 from the Unit 1 and 2 AP packet. This is again another no calculator question, and it says, let f be the function defined by f of x, another piecewise function. In this case, the overlapping region is at x equals 2. Part A says, determine whether f of x is increasing or decreasing at x equals 4. Justify your answer. By no means should you ever be referring to what does the graph look like, or what is the y value, or should you be plugging in points into f. When it says determine whether f is increasing or decreasing at x equals 4, we can only refer to the derivative being positive or the derivative being negative. So what you want to start off by is, what is the derivative? Well, the nice thing is with this problem, you can use the power rule on both the top and the bottom function. The power rule on top function, the derivative of 2x plus 1 is just 2 for all values where x is less than 2. For the bottom, you want to have the derivative of 1/2 x squared plus k, which in that case would just be x for all values x greater than 2. So now it says determine whether f of x is increasing or decreasing at x equals 4. So the only function I'm using is x, where x is greater than 2. To denote it, make sure you write f prime of 4 is equal to, and then 4. Now for me, this is simply just evidence. This is nothing else besides what is a derivative? Well, because f prime of 4 is positive, that means f is increasing. So that's what we need to write. Since f prime of x is greater than 0 at x equals 4, f is increasing at that point. You don't need to write out in words f prime of x is greater than 0 or f prime of x is positive. All you have to do is simply just have this statement down and then make sure you specify at x equals 4. So as far as points go on this problem was only worth 2 points. 1 point for finding what f prime of 4 equals, and then another point for answering the question. So moving on to part B, for what values of k will f be continuous at x equals 2? Because we're dealing with another continuity problem, we must use limits. Therefore, we want to start off by saying the limit of f of x as x approaches, in this case it's 2 from the left, must equal the limit of f of x as x approaches 2 from the right. Well, since we're going to use 2x plus 1, this is going to be 2x plus 1 evaluated at x equals 2, and this is going to be 1/2 x squared plus k at x equals 2, and they better be equal to each other if it's going to be continuous. So then, therefore, we plug in 2 for the left side, we're going to get 5. We plug in 2 to the right side, 2 squared is 4, half that is 2, so that's 2 plus k, and we get k equals 3. Again, this problem is only worth 2 points. Points come from you are showing that you are taking the left-hand limit and setting equal to a right-hand limit. And finally, do you have the correct value of k? For part C, this part's a little bit more difficult because it says, using the value of k found in part B, determine whether f is differentiable at x equals 2. Use the definition of the derivative. Now, it's really important that you are using the definition of the derivative to justify your answer. In order to prove whether a function is differentiable, once we know it's continuous, it's just not allowed to have a sharp corner there. So that means we have to make sure the left side slope is equal to the right side slope. Because it's important to read, and it says use the definition of derivative, we have to use the entire definition of derivative, which means f prime of a is equal to the limit of f of 2 plus h minus f of 2 all over h as h approaches 0. But because this is a piecewise function, we actually have two parts to this. We have the left-hand limit and the right-hand limit. So what we're going to do is we're going to start with the left-hand limit. So we're going to start with the 2x plus 1. So the limit of 2 times 2 plus h plus 1 minus, parentheses, 2 times 2 plus 1 all over h as h approaches 0 from the left, because we're talking about the gap being from the left side. If we simplify this, we're going to get 4 plus 2h plus 1 minus, and that's going to give you 5 all over h. Make sure to continue dropping down until it's evaluated at 0. You can't plug in 0 yet, so you hopefully simplify. 4 plus 1 is 5, which will cancel this 5. So then you're left with the limit as h approaches 0 from the left of 2, which is just 2. There's nowhere to plug in h once the h is canceled. So now for the right-hand side, the limit of the function as h approaches 0, now it's going to be from the right hand. Well, the function was 1/2 x squared plus, and the value of k was 3. So we will say 1/2 of 2 plus h squared plus 3 minus, and we want to use parentheses because we can't forget to subtract, 1/2 of 2 squared plus 3 all over h. We have to FOIL the 2 plus h squared. We have to simplify some other components. So limit as h approaches 0 from the right. This will be 1/2 4 plus 4h plus h squared plus 3 minus, and let's see, this will give me 4 times half is 2, so a total of 5. All over h. Continue to clean this up. If we distribute the half, we'll actually get 2 plus 2h plus 1/2 h squared plus 3 minus 5 over h, and then this is where the good things start happening. The 2 plus 3 will cancel out with 5. A lot of h's will cancel, one from each one specifically, and that will leave us with 2 plus 1/2 h. Now, since we can plug in h equals 0, we're going to be left with 2. So what does that mean for us? Well, left-hand slope is going to equal 2, and the right-hand slope is going to equal 2. Let's complete our idea. Since the limit of f prime of x as x approaches 2 from the left is equal to the limit of f prime of x as x approaches 2 from the right, therefore we have f of x to be differentiable at x equals 2. For the last part, D, let k equal 4. Determine whether f is differentiable at x equals 2. Justify your answer. Well, a lot of people want to do the same thing they did in part C, but now have a different value of k. Well, the most important thing about this problem is determine whether f is differentiable. The first thing says, if f is differentiable, then f must be continuous. That also means if f is not differentiable, then f will not be differentiable. So therefore, if we actually look from part B, it says, for what value of k will f be continuous at x equals 2? Well, then the value of k has to be 3. However, in part D, it says let k equals 4. So right away, we know it's not going to be differentiable because f is not continuous. So we can get away with saying, since f is only continuous when k equals 3, then f will be differentiable, or we can show it. And we really want to show it using, again, limits. The limit of f of x as x approaches 2 from the left will equal, well, the function was 2 times x plus 1 evaluated at x equals 2, which is 5. What's the limit of f of x as x approaches 2 from the right? Well, that was 1/2 x squared plus 1. In this case, it's plus 4, sorry, when x equals 2. And that's going to give you 8. Nope, 6. Well, how do we tell that it's not differentiable? Since the limit of f of x as x approaches 2 from the left does not equal the limit of f of x as x approaches 2 from the right, f will not be continuous at x equals 2, and therefore f will not be differentiable at x equals 2. For this problem, let's go back up, talk about point distribution. For C, the points add up to 3. 1 comes from the definition of derivative from the left-hand side. 1 comes from the definition of the derivative from the right-hand side. And then 1 is your final statement. And I sort of got cut off there at the end. This should say at x equals 2. For part D, this is only worth 2 points. 1 point for showing that the limit of the left is not going to be equal to the limit of the right, and 1 point for saying because they're not continuous, therefore the function will not be differentiable. Once again, the total is 9, as well as